Okay. You say something first about homework? Um, all right, so here are some new problems. The first one is one that I promised. This is actually kind of one of my favorite ones. Let R be any integral domain you want. Show the following conditions are equivalent. R is a proof for domain. And two, every overring of R is closed. One direction we kind of know from the stuff we've done in class. That is, if the easier direction if R is proofer, then every overring is closed. On the other hand, the other direction is kind of interesting. Show that if you have some domain and you happen to know that every overring is interval closed, it turns out to be proofer. That one, the 2 and plus one's a little bit tricky. So think about that. And you're going to need, I think, the fact that every overring is interval closed. That came up pretty heavily in what I did. So here's for the next one. What came up pretty heavily in what you did? The fact that every overring is interval closed, right? I mean, there's a place in the proof, or my proof anyway, that it's very clear why this is needed to be proofer. For the next one, I've got to give you kind of a little setup. So you can actually generalize my setup a little bit, but you have to be careful. I'm really good in the case where R is a PID. So suppose you have R as a PID, and let's suppose it's not a field, so it's an interesting PID. And let P be the ideal would be by P be a non-zero prime. So P is a prime element, it's not zero. So we're going to define a certain subring of the direct product. So what you can do is you can take R mod P squared, R mod P cubed, R mod P4 forever and ever, make the direct product of those, right? Now this is a big messy ring that's full of zero divisors. I think we would all have to agree, right? Z mod 2, Z mod 4, Z mod 8, Z mod 16. This is the direct product that's full of zero divisors. However, what we're going to do is we're going to take a particular subring of this direct product. This is called the inverse limit of R mod P to the NR. And so what I'm going to do is I'm going to take these cosets, R1 plus PR, R2 plus P squared R. So I'm going to take these cosets, but not just, I don't have complete freedom on cosets. Right. So it's all these cosets from the direct product such that the kth coset, so if you have RK plus P to the K and you have RK plus 1 to the K plus 1, then RK and RK plus 1 have to be equivalent mod P to K. So you can't just have complete freedom. Let me give you an example. I'll talk about an example of this in a moment. But anyway, so what has to happen is, for example, R2 and R1 have to be equivalent mod P, R3 and R2 must be equivalent mod P squared, R4 and R1 must be mod P cubed, and so forth. And this forms a ring with the inherited operations from the direct product. It's easy to verify when you sum 2 things in this form or multiply 2 things in this form that's still in there. So you should probably take a look at that. With that being given, let's suppose that R is a PID that's not a field, of course, for the K. P is non-zero prime. Show that this direct limit actually is a Noetherian valuation domain containing R as a subring. So even though the whole direct product is full of zero divisors, not only is this is a Noetherian valuation domain, and it contains R as a subring. Right? So in fact, one of the things that you might think is interesting about that is if you look at the direct product of Z mod 2, Z mod 4, Z mod 8, Z mod 16, all of these component rings have finite characteristic. However, this subring of the direct product must be characteristic 0 because it has to contain Z as a subring. Right? Characterize the units and the non-units in this inverse limit of R mod Pn. I think A will help you help with that once you know it's in the theory and evaluation domain. Let VP be the valuation on K induced by the ideal generated by P. Show that the function D from R cross R into the positive reals union 0 given by, and D is a distance function, by the way, D of xy is 2 to the minus VP x minus y if x and y are different. And 0 if x equals y is in fact a metric on R. Right, so it's a measure of distance that satisfies, well, D of XX is 0 if and only if, right, dxy is 0 if and only if x equals y, D of xy equals D of yx, and you've got the triangle involved. And finally, in part D, show that this direct limit thing, or inverse limit thing here is the completion of R with respect to this metric. Right? Now, I've actually captured several things in one, so let me say a couple of more words about this before we move on to the fun stuff we're doing. And this might help here. So, let me start with some kind of examples. So to give you sort of a feel for this problem here, somebody pick a prime. Don't make it too big. 5. What's that? 2? 5. Is there an argument here? What was the prime I didn't quite hear? What was it? 5. Let's go. So if you look at the limb, this set of R1, R2, R3, R1, R forever and ever, such that Ri say Ri. Well, actually, let me break this out because that'll be better. So this is the set of cosets 5Z R2 plus 25Z R3 plus 125Z RK plus 5K Z RK plus 1 plus 5 to the K plus 1 Z. So this is just something that you might find in the direct product of Z mod 5 and Z, but I can't give you complete freedom. I'm going to declare the so for example, the element and I'm to shortcut my thing, I'm just going to put bars on there to signify they're in. It's like 0 bar, 5 bar, 25 bar, 125 bar, 625 bar, hopefully all. This is not. Notice, by the way, that this is a zero divisor in the direct product, right? Because I can multiply this by 1. I can multiply, well, I can square it as a matter of fact, and I get 0. In fact, this is a nilpotent in the direct product, but this is not in. Because these are supposed to be equivalent mod 5, and they are. These are equivalent, right? These are supposed to be equivalent mod 25, and they're not, right? And these are supposed to be equivalent mod 125, so forth. So you've actually got a restriction, right? And in fact, somebody give me a seed here. Pick an element out of Z mod 5. 1. Okay. So this is in Z mod 5, right? So this next element comes from Z mod 25. Now I can't just pick anything I want. Tell me what elements out of Z mod 25 are kosher for going there.
1, 6, 11.
1 certainly.
16.
Right? These are the only things that are going to be equivalent to this mod 5. Right? I mean, I can't pick 4 bar, that's not going to work, right? Okay, let's pick one. Let's say 6 bar. Now, what are my choices? Well, now, whatever goes here has to be equivalent to 6 mod 25. So I could go 6 bar, 31 bar, 56 bar, 81 bar, and 106 bar.
Sorry for picking 5.
Right. Well, see, notice, just like the previous, I had 4 choices. Right? And so every next step, I will have 4 choices. So you can think of this like a decimal expansion, right? Where every new decimal point has 4 choices. Notice that this ring is uncountable, right? 5 choices. I'm sorry, 5 choices, absolutely. Everybody okay with the ring being uncountable? And in fact, anybody know what this ring is?
p-adic, 5-adic.
This is now I'm going to use the notation correctly. The 5-adic integers, right? Not to be confused with Z mod 5. This is the 5-adic integers. It is uncountable. It's an Ethereum valuation. I mean, but it's on the one hand, it's a very big ring, but it's very simple, right? Also, notice, can somebody explain how this contains the integers?
It just pop one number into all of the slots.
That's right. So we're gonna do some popping here. Any integer n embeds into n, and eventually, it'll get so big that it'll be smaller than the 5 to the n, and then it'll just continue being n, right? And so notice these things: characteristic 5, characteristic 25, characteristic, but this whole thing actually is characteristic 0. It's uncountable. Anybody want to guess what how you can characterize the units of this? This is kind of helping with the homework, I guess.
Each coordinate.
Right, that is correct. It would certainly have to be a unit in each coordinate, but there's a simpler way now that you've made that observation.
Has to have a unit first.
The unit in the first coordinate will do, right? As a matter of fact, the unit in the first coordinate, because once you have a unit, This thing's relatively prime to 5, every one of these are relatively prime to 25, 125, and so forth, so they're all units, right? And it's easy to show that you can actually construct the inverse. Okay, okay. So this is kind of an interesting ring that you can explore. By the way, here's another example of a PID. Take a field. And in this case, we'll let prime ideal P, the ideal determined by X. This is a PID that's still a maximal ideal. Let's see. Let's see if I can figure out my notation here. Guess what this completion is? You guys got the power to figure this out. What's that? There you go. And this one, you can dramatically see the decimal expansion, right? What do the units look like? Unit plus something times extra, et cetera, et cetera. Right? So look at that. So this is sort of the p-adics and the power series from polynomial ring over a field kind of all roll into one here. So hopefully this will be kind of a fun problem. Okay. Any questions? Okay. Yes.
What do you mean by the completion of R with respect to metric?
Like from analysis, right? I mean, so it's the collection of all Cauchy sequences, equivalence classes of Cauchy sequences like that. See, Michelle would be very proud of me, wouldn't he? Okay. Any questions? Okay, so the last theorem we looked at was 8.1.4. This is the characterization of ink, where ink holds if and only if for all prime ideals in the lower ring R and prime ideals in the upper ring T that contract to the original prime, then Q is maximal with exclusion to R minus P. These will come in handy here. Let me kind of throw this theorem at you. And this is why, you know, I said yesterday, you probably thought I was freaking out a little bit because I said I was talking more about integrality, and then I started doing all this business with going up and going down and so forth. Here's kind of a let R inside T be an extension of rings, T interval of R. Then R satisfies then T over R is both going up this is the big connection to integrality, one of them anyway. So if you have an extension that is integral, then it is both going up and it's ink, right? And we're going to get a nice result about integrality from here. So, and I also just remark, because I can't resist, that of course if it's going up, it's lying over as well. So let's see why this is true. We'll be using characterizations going up in ink earlier. previous couple of theories. So first of all, going up, we must show that if the so let me remind you that the characterization of going up is if you have a prime ideal going up if and only if you have a prime ideal from the base ring, and S is its complement, S equals 1 minus P, and Q and T, contracting P. Then Q is maximal with respect to exclusion of S.
Is that I C?
Is it?
Q is maximal with respect to infusion, exclusion of R minus B, then it corrects to.
Oh, yeah, it's right here. Yeah, so P is a prime ideal, S is a complement, which I've got that so far. And Q is a prime ideal maximal with respect to the exclusion of X. Right. Max with respect to exclusion of S, then Q intercept R, P, and ink should be the other one, right? That if it's fracts, then fracting then Q must be max with respect to exclusion. Q is max with respect to that R minus P. Okay, so we want to show if you have an integral extension, then T over R is both going up and ink. So if we're going up, we must show this. We must show that if you have if P is and Q maximal with respect to exclusion. That's so to this end, it must be the case that certainly it's true that Q intersect R is contained in P because Q, excludes the complement of P. And so that means that when you contract it down to R, you get some prime ideal that's contained in P. Right, so that's certainly true. Yeah, and of course, we want equality. If equality not hold, then we select some element of P that's not in that contraction. Find X in P, but not in Q intersect R. Right. And here I'm going to take advantage of the integrality. So since X is in P, but it's not in this contraction, if you throw X into Q, it must properly contain Q, of course. And what do we know about Q? Q is maximal with respect to the exclusion of X. So when you look at Q, the smallest ideal to contain Q and X, it properly contains Q, which was maximal with respect to the property of missing S. So it must hit S. So we can find a Q in Q and an A in T. Q, A, and T, such that Q plus AX equals S and S. Okay, so what do we know about A? Well, A is an element of T, and so by hypothesis, it must be integral over R. So I'm going to write an equation for integrality for A. And A is in T, and we must have a 0, 0, where our eyes are. So there's some equation of integrality that governs that A. So let's multiply this by X to the N. Multiply X to the N, didn't I? And of course, also keep in mind that X is actually an element of D, so it's actually an element of R as well. And this gives you an equation of integrality, because notice since X is in R, all these coefficients are still in R. No problem there. So this is an equation of integrality of the element AX. So let's massage this. AX is what? S minus Q. So if I replace AX by S prime to Q. And I replaced the R's times the X's with R hats, so I didn't have to write too much. And I can massage this. Let's see, where's the? Right. So this gives. Right. Equal to. Right, because this Q is actually Q. And so notice that when you multiply this out, for example, all the terms except SN are in Q. When you multiply this out, all the terms except the leading term are in Q, and I've just sort of redone this. All right, everybody okay with that? And so, if you look at the above left side, this is in all the terms over here are in R, and all the terms are in Q. At the left side. That's the problem. Let's do it this way. Okay, so right. Notice that all these terms here are in. Yeah, they're certainly all in R, because this is in R, and they're in Q, except for this one front. So these terms are all in R, and they're all in Q, because all these coefficients, in fact, are in P. Right? Maybe I should have left those X's in here, but remember, X is in P. It's in P, so all these middle terms are actually in P as well. Because all these are in R, and all these powers of X, they're in P. So these things are all in P here.
But you don't necessarily know that P is contained. That's what we're.
Q and R is Q intercept R.
Yeah. Okay, so, this bit is in R intersect Q, which is P. And so S.
It should be contained.
Okay, so what's the point of confusion here?
R intersection Q equals P, that's what we're trying to show.
R intersect Q is contained. in P. I'm sorry, you're right, I shouldn't put that. This is all I need. Because this bit, all of these things are in R. And they're all in Q, so they're all in P, right? Because all these coefficients really had an X multiplying them.
The next was in my P, but not a Q.
Yeah, that's right. No, X is in P, but it's not in Q intersect R. Right, X is in R because by the fact it's in P. It's just,
So how do we know that that's a Q?
well, it doesn't matter. I mean, I wrote the same. These are all in P for sure.
Okay.
Right. Okay, so, so where does SN lie? SN is the difference between this Q1 and Q and this in P. Okay, so, so SN is in Q.
Well, Q1 is also in R because all of the terms on the left side.
Yeah, that's right. So Q1. That's right, because Q1 is actually a Q, but it's in, Q1 is in Q, but of course, these terms are all in R, so this is contained in P as well. So this bit is in P, this bit is contained in P, so Sn minus one. Or so Sn must be contained in P, right? And this is a contradiction. Because of course, this is a multiplicative of a closed set, so, in fact, you can assume it's set, yes.
Why are you saying this guy is in P?
Because it's the same as this. Right, and notice that AX, well, so these are all in R and the X's are in P, right?
Yeah, but AX is not in R. This A is not in R. Right, A is in P. So it's not even, I wouldn't even expect it to be in R in the first place.
All the coefficients are.
Yeah, yeah, that's right. It's the coefficients that I'm talking about are in P right here. So,
But S minus Q not necessarily.
S minus Q, not necessarily, right? So the coefficients are in P.
Like the R and minus one to next X becomes R.
Each RI bar is in P. There we
Yeah.
go. Which is all we need because up here, this gets you P and P.
Our bars and R are the same.
Yeah, I should have said, notation. So let's see. Let's see if I can butcher the other one just as much. So now what we want to do is show, so we've got, this gives. While it's going up. So. What about, ink? Well. Learn a lesson here. Let me scribble down the ink again. Ink means, that. Ink if and only if. For all primes. And Q and T contracting. T. The Q is maximal with respect to the complement, then. Q is maximal. With respect to exclusion. Of S. Okay, so, how are we going to use the ink here? Well, assume that P is the contraction of Q. We need to show that Q is maximal. With respect to exclusion of S. So, if not, then Q is contained in some ideal I properly, such that I intersect S is empty. This is what it means to not be maximal with respect to the exclusion of S. I can find some larger ideal I, in fact, I can force it prime, such that I intersect that S is empty. So let's let U be, and I take away Q. And again, I'm going to use the fact that U is integral. It's an element of T, which is integral over R. So U is a root of a monic polynomial with coefficients in R, right? So among all F and Rx, such that F of U is in the prime Q. This is kind of I did say monic, didn't I? Yes. Among all monic polynomials such that F of U is, well, we know that there are monic polynomials such that F of U is equal to 0, right? That's what it means to be integral. I'm going to generalize this. A generalization of F of U is 0 as F of U is in the ideal Q. There must be at least one monic polynomial that satisfies this. In fact, monic polynomial that makes this integral. And among all monic polynomials such that this is in Q, we select one of least degree. So F of U is in the ideal Q, and no monic polynomial of smaller degree has this property. Note degree of F of X bigger than 1. Why?
That would be in Q, U would be. And
Right,
Q
because
is
it's
what-
monic of degree 1. Yeah, you'd be in trouble there. Okay, so let's suppose our polynomial, well, our polynomial relation is. So u to the n, so Rn minus one. Or our, well, our polynomial. This. So that's gotta be, of course, the output of that's gotta be in Q. Notice that. Anybody make an observation about the constant term here?
I can't.
Well, I think it,
All you can use are in I.
would everybody agree with that? That R zero must be an I? Right, because all the U's are in I, so this is a big fat thing in I. And this is in Q. Right? So what can we say therefore?
Also in R, so it has to be. Wait,
So R zero is in I and in R, right? And so that means that it must be in P. Right, because I is actually an ideal that misses S. So when you contract that back down to R, it's contained inside of P, right? And of course, P is inside of Q. So R zero, so R zero is an element of Q. And so hence, so R zero is in Q, and this is equal to an element of Q. So what's left over that must be, which means that product's Q. Now, by hypothesis, and of course, Q is a prime ideal, so one of these two things has to be in here. By hypothesis, U is not in Q. And this can't be in Q either because it's a lower degree monic relationship. So. Hence.
is substitute.
So which one now?
I understand R is in P.
Right. I intersect S is empty, right? So that means that, right. And remember what S is, it is the complement of P. Right, so you intersect I into R. It must be contained in P, right? Because there's no overlap with S, so it has to be contained in the complement of S, which is, does that clear it up a bit?
Yeah.
Okay. Any other questions? There's another offshoot of this we'll talk about next time. It turns out that, how many of you have heard of crawl dimension before? I know a couple of you have. It's basically a way of measuring how big your ring is. It turns out that if you have ink and going up, then you preserve crawl dimension. So integrality preserves that as well. We'll see that next time. Any questions? All right, well, I will see you all on Friday.